In this video, we're going to talk about section 6.4. We're interested in looking at irrational and real numbers, but to kind of really do justice on that discussion, we first need to talk about square roots. So I'm going to do this by example. I feel like that's a good way to do it. So like, for example, let's find the square root of 4, which means what number squared is 4? And I hope that you immediately know that's 2 because 2 squared, or 2 times 2 is 4. Okay, cool. So, technically, there is another answer that works. Technically, -2 squared is also going to be 4 because -2 times -2 is 4. But we never really consider the negative number when we take a square root. And the reason is when we work with square roots, we're typically working with what's called the principal square root. So when we're asked the square root of a number, they're usually asking for the principal square root, which means they want the positive answer only. Now, there are cases where they might ask for the negative answer too. Usually, rather than say square roots, they might say the roots of a number. And then, of course, if we introduce a square root, we'll talk about maybe the possibility of what a negative would be in those examples, meaning we won't necessarily assume we're working with the principal square root, but sometimes we will, and we'll talk about that. Okay, let's just do some more square root examples just to feel good about square roots. All right. Let me go ahead and give you like a list of problems to try here. We'll do like a part A. And if you want to pause the video and give these a try, go for it. And then we'll do, oops, sorry, this is part B. And then part C. Here, we'll make them a little more interesting. Throw a decimal in there. And if we're doing a decimal, might as well do a fraction. Okay, 4 parts for you to try. Go ahead and if you want to pause the video, give them a try, go for it. But we'll go ahead and talk about them. So square root of 9, that's 3. And the reason is 3 times 3 is 9. I'm not going to write that down, but that's the reason. Square root of 64 is 8, since 8 times 8 is 64. Okay, now the square root of 0.49, I hope you notice that 49 itself is a number that we can find the square root of pretty easily, right? So the square root of 49 is 7. And then since there's a decimal, we have to think about it. 0.7 actually does work because 0.7 times 0.7, when we multiply 2 decimals, we count how many numbers are behind the decimal. So there's 2 numbers behind the decimal. And then 7 times 7 is 49. And then we need to make sure that there's 2 numbers behind the decimal in the answer. So we put our decimal in front of the 49. So there we go. So 0.7 is in fact the answer for 0.49. 1/4. Okay, so 1/4, it's easiest with fractions to go ahead and consider the numerator and the denominator separately. So, and in fact, I encourage you to even break it up as thinking of it as the square root of 1 over the square root of 4. And the square root of 1 is 1. Square root of 4 is 2. And there you go. So there we are. There's some fun square roots for us. Now, part of what made these not too difficult is that every single number here is what we call a perfect square. So these are numbers that come from squaring, okay? So the first number that's a perfect square is the number 1 itself, because 1 squared is 1. The second number that's a perfect square, well, that would be 4, since 2 squared is 4. And then would be 9, 16, and if you want to pause the video and finish writing them, 25, 36, 49, that's 7 squared, 8 squared, 64, 9 squared is 81, 10 squared is 100, 11 squared is 121, and then 12 squared, 144. And there we go. Those are the perfect squares you are expected to know. There are different variations on the perfect squares you probably should know, like 40 squared is 1600, right? If you take one of these perfect squares and throw a 0 on there, you should be able to find the perfect square of that number, okay? But these are the basic perfect squares you're expected to know. Now, couple comments we're going to kind of look at here. They have what they call in the book the square root squaring property. And that's the idea that if you take the square root of a number and times it by itself, that ends up canceling the square root out. And the reason is, another way of thinking of this number here is the square root of a squared. And if you square the square root, it's going to be the number itself. Okay. So they call that the square root squaring property. Then there is kind of an interesting, let's say, divergence we should take at this moment and look at non-perfect square numbers. Okay, so for instance, the square root of 2 is not a perfect square, and I can't take the square root of 2 without using the calculator. In fact, I encourage you, grab your calculator. Let's find the square root of 2. We'll come up with a decimal approximation. It'll be good for you to kind of learn how to enter that in your calculator. And if you plug it in correctly, let's see, let me go with red here, you should get 1.4142. Okay, so we'll just round to 1.41. Okay, I'm sorry, 1.414 is what I meant to say. So that's the square root of 2. We can't simplify it any further. All right, as a square root, that can't simplify further. We can only plug it into the calculator. But it is possible in some cases to do some simplifying, okay? For example, in here, I want you to kind of leave a little space, or don't write it until I write what I'm going to put in the space here. I could actually simplify the square root of 20, okay? And the way I do that is I look for perfect squares. So this uses an idea where if you have the square root of a times b, that can be thought of as the square root of a times the square root of b. It goes both directions. In other words, if I have the square root of a number times the square root of a number, another number, we just multiply the two numbers together. Or in this case, I'm going to use it in reverse. If I have two numbers under a square root, I could break it up into two square roots. And the two numbers I'm interested in for the square root of 20 is the square root of 4 and the square root of 5. And the reason is 4 is a perfect square. I can simplify the square root of 4 as 2, and then 5 would stay under the radical. Let's try another one. Let's find the square root of 75. If you want to pause the video and do it real quick, go for it. But the perfect square that I see that goes into 75 is 25. So I could think of this as the square root of 25 times the square root of 3. And square root of 25 is 5, and then square root of 3, I can't evaluate. So that would be the answer. I would take a second again, grab your calculator. Let's find a decimal approximation for each of these. I want to kind of practice with how to plug that into the calculator a little bit for applications. It's kind of good to know how to plug into the calculator. Okay, so to find this in the calculator, you first start by taking the square root of 5 and then timesing it by 2 on some calculators. Some calculators you can enter it exactly as it is. But if you do it correctly, in here I'm going to round to the tenths place. This would be about 4.5. And then the square, 5 times the square root of 3, that would be 8.7. So make sure you get those numbers from your calculator. And if you have any trouble, let me know. I'll be happy to help you. Okay, so there's how we simplify square roots when we can't completely simplify them. If we can find a perfect square, that's what we'll do. Otherwise, we have to jump to the calculator. Now, this leads to a wonderful application called the Pythagorean theorem. Most people have heard of this, of course. It's probably the most famous theorem in all of mathematics. Pythagorean theorem. Oh, wow. Which I spelled wrong because I looked at my page while I was writing. Sorry. Pythagorean theorem. Okay. So Pythagorean theorem only works when you have a right triangle, meaning a triangle with a 90-degree angle. I'll just kind of draw my triangle like this, pretend that's straight. I've talked about how it's hard to do straight lines on this drawing pad. And we indicate the right angle or the 90-degree angle with the little square in the corner. Okay, lovely. We label all the sides of the Pythagorean triangle. The important part are the sides that are adjacent to this right angle. These two sides we're going to call A and B. By the way, those two sides, they give the name legs. But the side that's opposite of the right angle, that's side C, and that's also important. That one we call the hypotenuse. And I hope this terminology kind of comes back to you because I'm pretty sure you've seen it at some point. And the Pythagorean theorem itself is a squared plus b squared equals c squared. The history of the Pythagorean theorem is pretty extensive, and there are lovely proofs. In fact, I will do another video. Either I'll link one or I'll make one on a proof of the Pythagorean theorem. There's just so many beautiful proofs of it. But let's use it. Let's go ahead and practice the Pythagorean theorem itself. So let's say I have a right triangle. Something like this, okay? And let's say that this is 8 and this is 6. And I'd like to find the missing side there, okay? So based on my labels, 8 would be my hypotenuse, 6 would be one of my legs. And I could go ahead and call the missing side, I'll call it B, but you could call it A. A or B would probably be very appropriate. Actually, you could call it X if you want it. But I'm going to label that missing side. I'll go ahead and just call it B for right now. And according to the Pythagorean theorem, 6 squared plus b squared equals 8 squared. 6 squared is 36. 8 squared is 64. So to solve for b, I need a minus 36 from both sides. Let's see, what does that give me? Is that 28? 64 minus 36. Yeah, I got 28. So to solve for b, we need to go ahead and take the square root of both sides to find what b is. And then in order to take the square root of 28, I'm going to break it up. The perfect square I know that goes into 28 is 4. So b is 2 times radical 7. And that's how we can use the Pythagorean theorem to solve for a missing side of a triangle. Let's do another one. Let's try this time like this. Okay, so this one they give us 12, 13. Missing side again is down here. I'll go ahead and call it A this time, just so you know that it doesn't really matter. Okay, so A squared plus 12 squared equals 13 squared. So let's see. Oops, 12 squared is 144. 13 squared, if you grab your calculator, is 169. So I'm going to subtract 144 from 169. And that's going to give me, let's see, 25. Well, that's nice because when I think of what squared is 25, right? It's 5. So sometimes they come out nice. Yay. And sometimes they don't. And we just look for a perfect square if we can. If we can't find a perfect square, we leave it alone. Okay. So if there isn't a perfect square in there, we just don't simplify it any further. It's fine. There we go. So there is some examples using the Pythagorean theorem. Now I want to do one actual example that could be kind of useful as an application. So I'm going to refer to problem number 36 in the book on page 397. And it has a picture. So I'm going to go ahead and I copied it. So let's see if that comes in pretty nicely. Give myself some space here. And paste. Ah, not too bad. All right. So this is a picture of a baseball diamond. And they are asking how far from the mound, from the center of the mound to the second base. So the mound is what they're indicating right here with this. And basically, they're asking us to figure out the distance from here to here. All right. So I'm going to go ahead and call it X. Now, because we just talked about the Pythagorean theorem, I hope you see we actually have two right triangles, right, in this baseball diamond here. And we'll just use one of them to find the full diagonal going from home base all the way to second base. Okay, so let's do that. 90 squared and so the 90s are the legs, right? 90 squared equals, okay, so here I'll call it C squared for right now because I'm not finding what the X, right? X is just part of the hypotenuse. So here I'll call the hypotenuse C, referencing what we did in the Pythagorean theorem earlier. Okay, so 90 squared is 8100 plus 8100 equals C squared. All right, and I'm getting, oops, I added that wrong. Hold on, 8100, 8100, there we go. Okay, 16,200 equals C squared. Now, the book actually says round the answer to the nearest foot, meaning that they understand that our answer is going to be a decimal approximation. So they're kind of letting us know that the square root of this, don't bother simplifying it. Go ahead and just plug it into the calculator and get a decimal approximation. So when I do that, I get 127. We'll do 0.3 for right now. I know we're going to round to the nearest foot, but I mean, they used 0.5 for the distance from home base to the mound, the pitching mound. Okay. Okay. So then to find X, X is going to be 127.3 minus 60.5. Oops. 60.5. Okay. I'm getting 67. Oh, wait, no, sorry, 66.8. Well, yeah, that's rounded. Sorry, not rounded. I mean, I did the calculator without rounding. Let me do it with the rounded answer. Okay, sorry, 62.8 is what we get if we plug literally what I just wrote into the calculator. So we can round that to 63 feet. All right, so there we go. That's how we can use the Pythagorean theorem to actually answer real world questions. And we're going to, from here, I'm going to do a separate video on how this kind of brings us to irrational numbers and the real numbers.